Have you ever wondered what hazards are in digital logic and design? In this context, a hazard is a potential glitch or inconsistency that can occur during the operation of a digital circuit, particularly when it transitions between various states. These hazards can cause incorrect outputs or unexpected behavior, which can be problematic for the overall circuit operation. There's a variety of hazards that can occur, but they primarily fall into two categories: static hazards and dynamic hazards. Static hazards are often associated with races, instances where signals have differing delays through a circuit. Dynamic hazards, on the other hand, manifest as glitches in the output waveform and can also occur due to races between signals. Each type has its own unique characteristics and potential impacts on a circuit's performance. Understanding these hazards is vital to ensuring a digital circuit operates as intended. Let's dive into the first type of hazards: static hazards. Static hazards are closely tied to an event known as a race. Imagine a race where the competitors are electric signals navigating through a circuit. These signals don't always reach the finish line, which in this case is the output at the same time. This mismatch in arrival times can cause the output to briefly display an incorrect value, or a glitch, before settling on the correct one. Now, let's differentiate between two types of static hazards. First, we have the one hazard, also known as static 1. This happens when a change in one input causes the output to momentarily jump to 1, before returning to its correct value. On the flip side, we have the zero hazard, or static 0. This is a mirror image of the one hazard, where a transition in one input causes the output to momentarily dip to 0, then return to its correct value. To illustrate, imagine a digital circuit with two inputs, A and B. A transitions from 0 to 1, while B remains at 1. If A takes longer to transition than B, the output may briefly switch to 0, even though the correct output is 1. This momentary dip to 0 is a zero hazard. Similarly, if B transitions from 1 to 0 while A remains at 1, and B takes longer to transition than A, the output may momentarily switch to 1, even though the correct output is 0. This fleeting jump to 1 is a one hazard. Static hazards, with their brief glitches or undesired outputs, are a critical issue to address in digital logic design. They can cause circuits to behave unpredictably, leading to errors that might be hard to detect, but can have significant impacts on the functionality of the digital system. Therefore, understanding static hazards is a vital step towards creating reliable and efficient digital circuits. Now, we move on to dynamic hazards. Dynamic hazards are quite the characters in the world of digital logic and design. These hazards arise due to races between signals, much like static hazards. However, there's a twist. Dynamic hazards manifest as glitches in the output waveform, rather than causing the output to temporarily go to an incorrect value. Imagine this scenario. You have a digital circuit where different signals are racing through, each taking its own path. Now, due to the varying lengths and properties of these paths, the signals don't arrive at the finish line, that is, the output, at the same time. This misalignment in their arrival times can cause the output to fluctuate, creating what we call a glitch. This is the essence of dynamic hazards. But that's not all. There's another type of dynamic hazard known as the minterm hazard. This hazard is particularly crafty. It occurs when a minterm in the sum of products expression of the circuit changes value during transitions. To illustrate, let's consider a simple example. Suppose we have a sum of products expression that includes the minterms ABC and ABC. If there's a transition from ABC to ABC, the output should ideally remain constant. However, if there's a slight delay in the arrival of the B signal, the output may momentarily drop to 0 before bouncing back to 1. This brief flicker is a minterm hazard. Therefore, dynamic hazards can be quite disruptive. They can cause glitches in the output waveform, leading to incorrect or unexpected circuit behavior. But fear not. In the world of digital logic and design, we're equipped with an array of techniques to tackle these mischievous hazards. We'll dive into these solutions in the next scene. Dynamic hazards can cause glitches in the output waveform, which can lead to incorrect or unexpected circuit behavior. Hazards are not limited to just static or dynamic types. They can also occur in different kinds of circuits. Let's delve into the world of combinational and sequential circuits to understand how these hazards manifest. Combinational circuits, as the name suggests, combine various logic gates without any feedback. In these circuits, hazards can emerge due to mismatches in signal arrival times, leading to temporary signal imbalances. Picture a combinational circuit with multiple inputs affecting a single output. A change in just one input might cause a momentary incorrect value on the output before it settles to the correct value. This fleeting error is a hazard that can disrupt the circuit's intended operation. Now, let's shift gears to sequential circuits. These circuits differ from their combinational counterparts as they have feedback loops and clocked elements. In this environment, hazards can arise during the transitions between clock cycles. These transitions can result in temporary inconsistencies in the state of the circuit, causing the circuit to behave unexpectedly. To illustrate, imagine a sequential circuit with feedback elements. As the circuit transitions from one clock cycle to another, the output might not immediately reflect the correct state due to the delay in the feedback loop. This delay can cause a temporary incorrect output, leading to a hazard. But why should we worry about these hazards? Well, in digital systems, even the slightest of errors can have significant consequences. An incorrect output, even if it's temporary, can trigger subsequent circuits prematurely or cause erroneous readings, leading to overall system failure. So it's crucial to identify potential hazards during the circuit design phase and take necessary steps to mitigate them. This not only ensures the reliability of the circuit, but also enhances the overall performance of the digital system. In conclusion, hazards in combinational and sequential circuits can be as detrimental as static or dynamic hazards. They can lead to temporary inconsistencies in the state of the circuit, which can cause unexpected circuit behavior. However, with careful design and hazard mitigation strategies, these hazards can be successfully managed. Now that we know the problems, how do we solve them? Let's delve into the various strategies that engineers utilize to mitigate hazards in digital circuits. First up, we have the addition of delay elements. This solution involves introducing controlled delays into specific paths of the circuit. The goal here is to balance the signal arrival times, ensuring that all inputs reach their destinations in sync. By carefully controlling these delays, we can prevent the momentary glitches caused by static or dynamic hazards. Next, we have the use of hazard-free circuits. This isn't about making the circuit invulnerable. Instead, it's about designing the circuit in a way that inherently avoids hazards. These circuits are crafted with built-in prevention mechanisms, ensuring that hazards are far less likely to occur in the first place. But what if you've already got a circuit that's playing up? Well, this is where optimizing logic expressions comes in handy. This solution involves minimizing or simplifying the logic expressions that define the operation of the circuit. By reducing the complexity of these expressions, we can decrease the likelihood of hazards occurring during transitions. Let's consider a practical example to put these solutions into perspective. Imagine a circuit with inputs A, B, and C, and the output is defined by the logic expression F equals sign ABC plus ABC plus ABC. If a hazard occurs due to transitions in these inputs, we could apply any of the solutions discussed. We could add delay elements to balance signal arrival times or optimize the logic expression to simplify the circuit's operation. Remember, the goal here is not to eliminate every single hazard. That would be an impossible task. Instead, the aim is to minimize their impact and ensure that our digital circuits operate as intended. By implementing these solutions, we can significantly reduce the impact of hazards and ensure the correct operation of our digital circuits. So, we've learned quite a bit about hazards in digital logic and design today. We've delved into the nitty-gritty of static hazards, understanding how races and signal delays can cause those pesky glitches and unexpected outputs. We've also observed the dynamics of dynamic hazards, where signal races can manifest as hiccups in the output waveform. We've explored how hazards rear their heads in both combinational and sequential circuits, and how changes in inputs and transitions between clock cycles can lead to temporary inconsistencies. But fear not, we've also discovered effective solutions to these hazards. Remember, adding delay elements, employing hazard-free circuits, and optimizing logic expressions can significantly mitigate these issues. We've seen how a simple circuit with 3 inputs could potentially produce a hazard, and how we could address it. Understanding and mitigating hazards in digital logic and design is a crucial part of ensuring reliable and correct circuit operation. Keep exploring, and you'll become a master in no time.